Alright, so the next concept related to memory management which we are going to be looking at is called swapping. So, for a while now we've been seeing about main memory and logical memory. So, when we saw paging, we looked at that quite in detail, right? So, at the very beginning of our discussions on paging, we we familiarized ourselves with this notion that your data exists, your processes exist in your logical memory. When you want to execute something, you bring it to the main memory, then you execute it, you read, write, update, delete, you do whatever you want to do, then you put it back in the logical memory, right? This much we are familiar with from our discussions on paging. Also, from our discussions on scheduling and all of that, we know that when a process is being executed, it will be taken up by the processor and it has some memory space. And then when it is no longer being executed, either it has been terminated or it has been temporarily paused for some reason. You remember the process states diagram we saw, right? There is this state called ready, there's waiting, there's running, and so on and so forth. So if it is temporarily paused for some reason, you remove that process from the memory and you bring in some other process. So that thing is switching is called a context switch. We also know this. So let's put both these pieces of information together and let's try to get a picture of what is happening with the process. So my process is somewhere in the logical memory. I decide that I want to execute this. So let's call this process P1. So I decide that I want to execute P1. So I'll bring P1 onto the main memory. I allocate some space to it, either using variable partition scheme or paging. Some logic, I'm allocating main memory space. And then P1 is ready for execution. It goes to the ready queue. The scheduler picks it up and assigns it to a processor. The processor now accesses these memory locations and it starts working. Well and good. Now suddenly either there is an interrupt or for some reason P1 is stalled, or the simplest reason could be that you are working on a round robin scheduling algorithm. So after every time quantum has expired, that process is stalled and the next one is picked up, right? So for some reason like that, the reason is not going to be the focus right now. For some reason the process is stalled. Now the processor will obviously kick this P1 out of the memory and take some other P2, right? And then later when I want to execute P1 again, P1 is brought back into main memory, it is executed. So that continues. So now during this time interval when P1 was temporarily stalled, when it was kicked out of the main memory, it could have been put back in the logical memory. It is a perfectly sensible thing to do and perfectly possible as well. But what happens is, every time if you're going to keep making a trip between the logical memory and main memory, it is time consuming and expensive, right? So a better idea would be if you have a temporary container kind of thing nearby, and if you know you're going to need this soon in a very short period of time, if you could put that data in this temporary container and then take it back when you need, that makes more sense, right? The simplest analogy would be if you have let's say a 20-minute break and you're stepping out of class, you leave your bag, your laptop, most of your things there inside the classroom. You'll put your stuff inside your bag, you'll close your bag, all that of course, but you're likely to leave your bag in the classroom because you're going to be back in 20 minutes for the next class. Whereas let's say you're going to attend a 3-hour lab session, then it is likely that you will carry your bag, your laptop, everything to the lab and go, because in that case you're not going to need these things for a long time. So it makes sense to take it and put it back where it's supposed to be, right? But if you know that in 20 minutes I'm going to be needing this again, then instead of taking it all the way to, let's say, your hostel room or whatever, you would rather leave your stuff in your classroom itself. So in that sense, even though you're out of the classroom for that 20-minute interval, the classroom is acting like a temporary repository or a container where you put your stuff, right? That's the idea I'm trying to convey. So I'm executing P1, I'm stopping it for some reason, but I know I'm not done with P1 yet. I know I'm going to need P1 very soon again. So instead of putting it back in the logical memory now, and then again when I need it within a few clock cycles, again I have to go all the way to the logical memory and bring it back. Instead, if I have a temporary container where I can put P1 right now, and then when I need P1 again, I'll take it back from here. It is going to save me time, it is going to save me computational resources. So this temporary container is what we call backing store, and this process is called swapping. So what is swapping? When you're working on processes, you've not finished yet, but for some time you want to remove this process from the main memory and accommodate some other process. You will put the process you kicked out in a temporary container called the backing store, and then you will accommodate some other process, you will work on it. Once you're done with that process, you will put that in the backing store and take this back, right? So this temporary exchanging is what we call swapping. So a quick terminology alert: swap out is when you take something from the main memory and put it in this backing store. Swap in, vice versa, you take it from the backing store, put it back in the main memory. So what happens now? P1 comes from logical memory to main memory, gets executed. At some point execution is temporarily stopped, P1 goes to the backing store. Some other P2 is taken either from the backing store or from the logical memory depending on context. P2 is executed. Now P2 is either completed or P2 is stalled. For some reason the CPU decides I want to continue with P1. It goes to the backing store, it will quickly take P1, come back, work on it until P1 is terminated. Once everything about P1 is done, it goes back to the logical memory. So this temporary storage is what we call the backing store, and putting your processes there is what we call swapping. So within swapping you have subtypes. The first one is called standard swapping, which is the simplest, the most basic idea, and that is exactly what I've described over here.